Thank you guys for coming. My name is Charles King. I'm the previous director of UPE Make. Yeah, today's workshop is going to be TinkerCad workshop, where we're going to be covering circuits, microbits, and Arduino programming. So if you don't have a lot of knowledge or experience with programming, microbits is going to allow you to get a little bit more familiar with it. And then we're going to go a little bit more in depth with actual programming with Arduino. So yeah. If you want to get connected with CAHSI, or I think that's how you pronounce it, this is our and the website, or the QR code. And also, I should mention this is in partnership with UPE and SHPE. So, yeah. Again, what we're going to be covering today is going to be circuit analysis, microbits, and Arduino programming. So, it's going to be some pretty interesting stuff. Starting off, so what is a circuit, right? A circuit is basically where you have a path of conductive wire or something where electricity could pass through. And with that, you have voltage, you have current, and you have resistance. With voltage, basically what it is the amount of potential energy between 2 points on the circuit. So say, for example, you were to measure the amount of voltage that is on this side of the wire and this side of the wire. There's going to be more electrons on this side than there are on this side at that point, and that's going to be measuring what the voltage is. Now, something to realize about circuits in general is that the conventional current that we all know goes from positive to negative. But in actuality, the electrons that are flowing through a circuit are going in the opposite direction. So these are electrons or negatively charged, and they go towards things that are positive because opposites attract, right? So even though the conventional current that we're always told is going from positive to negative, just keep in mind that the actual motion of which way the current or the electrons are moving are in the opposite direction. Another thing to mention is what is a current. So current is basically, again, the electrons that are moving within a wire, and for that current to be flowing, it has to be closed. Sorry. So yeah, and then what's resistance? Resistance is when you have an opposition to that current that's flowing in a circuit. So when you have 2 points in a conductor, take for example a light bulb or a resistor, those things are taken away or making it harder for those electrons to pass through, which is creating resistance. While there's a potential difference across a conductor, that encourages the flow of electrons, but when you have a resistor, it discourages. So those electrons are being not easily able to pass through. Now to talk to you a little bit about the different types of connections that we have with circuits. There's two that are the most important to know. One of them is series, and then the other one is parallel. In the series connection, this is what a series connection is, where you have your battery and then you have two bulbs or resistors that are in the same path. So whenever you have two components that are connected in the same path, what that means is that the current is always going to be the same between those two components. But what happens is that since these two components have resistance to them, their voltage is gonna be dropping from the transition of one side of the wire to the other. So that's how you can kind of understand how voltage is the difference of potential energy from one point to another. The voltage that's going to be at this point and at this point is going to be different because the voltage that's needed to power this light is going to be taken from that component. Now, something else to consider is if we look at this analogy right here, it's an analogy so that you could understand more how voltage works and how current works. So with the voltage, you can see here that you have a tank of water, basically. The amount of water that's in here could be looked at as the charge, and then the flow, I guess, of the water going through this part of the tube to the top. There's a lot more potential energy on the top of the tank compared to the bottom. So that's how you can see that there's potential on the bottom of the tube and then on the top. compare, and also like with current, similarly, if you have a tube that's more wider, you're gonna have more water going through it compared to one that's smaller. You're gonna have less, so that there's gonna be less current or less electrons in like, if you were to look at it as an analogy. And then with resistance is the same thing. You have things that are resistance the path of water going through there, in which case is making it harder for the water to pass, or similarly electrons. One other important thing to consider is the Ohm's law. Ohm's law is basically the way it's a formula that's used to understand the relationship between voltage, current, and resistance. So this is a triangle that's very much used whenever you're doing circuit analysis. And it's used so that you could understand what it is that you have to multiply or divide, so that you could get that value that you're trying to get in the circuit.
That's true.
So if you look at this example, we're gonna start with this example. If you guys want to get a paper or just pull out your calculator on your computer so you can follow along, great. But I'm gonna go ahead and ask you guys. We have a 9-volt battery here, and we have 3 resistors. Since we have 3 resistors and these resistors are in series, that means that the current between all these components are going to be the same. But throughout each component, the voltage is going to be dropping. Now, does anyone in the audience or in the group know how it is that you add resistors in series?
In series, they just add, right?
Yeah, basically. So they just add. So if you want to get the resistance equivalent of the whole circuit, you add one resistor with the other. So R1 plus R2 plus R3 will give you the resistance of the whole circuit. Now in this case, we have 10, we have 3, and we have 5. So that's going to give us 18 ohms of resistance. And that's the unit that's used when we're measuring resistance, is ohms. Now that we have the resistance equivalence of the whole circuit, and we also have the voltage, I'm going to ask you guys again, what formula will we use to find the current of the whole circuit, over the whole system? If you look at this triangle up here, then you might be able to remember. V divided by R. Correct. Yeah. So V divided by R gives you the current. Since we have the resistor equivalence and we have the voltage,
you got 0.5 amps.
Exactly. So this is the current that's flowing through the whole circuit. Again, this is a series circuit, so the current that's going through every single resistor is going to be the same. What's going to be different is the voltage that's passing through each circuit, because at the end of the circuit, we want there to be 0 voltage, and basically that's how you're checking the difference in potential. If you were to put a multimeter with the positive end on here and then the negative end here, you would get 9 volts, because throughout this whole resistor, the voltage is dropping. So I'll give you guys the first one, but if we want to get the resistance or the voltage of the first resistor, then we're going to get that current that we have and multiply by how much ohms we have of resistance, which is going to be 1.5. Now let's go ahead and, if you guys want to follow along, for the second one we have 10 ohms and we have the resistance, which is 0.5. If we were to multiply that, it would be 5 volts. So far we have 5 plus 1.5, which is 6.5 volts. So we could assume that the rest of the voltage is going to be dropped from this last resistor, which is going to be 2.5. If we add these voltages together, then we get the total, which is 9 volts, which is the amount that was dropped between all the resistors. Now, to show you that how this actually works, we're going to actually... Let me sign in. I don't know why I was signed out really quick. But while I'm doing this, go ahead and go to tinkercad.com. And if you haven't made an account, make an account with your student account or your student email. And then let me log in while you guys are doing that. So what we're going to be doing is that we're going to actually show you how we could measure that and show you that the theory of the series connection is actually true, in that the current stays the same and the voltage drops. And then after that, we're going to cover parallel circuits. And then we're going to start programming with the macro bit and the Arduino. Okay, so now that we have, hopefully you guys have TinkerCad open, we're gonna go to the circuits tab and we're gonna create a new circuit. So the cool thing about TinkerCad, not only that it gives you the ability to create circuits, but you also have 3D models and programming as well, which is a super good tool, even now that we are in virtual and some of us can't afford an Arduino. But I would say the Arduinos are really, really cheap. So if you do want to get one, you could probably look online for one that's 10, 15 bucks probably. So where we're going to start off is we're going to get a battery, 9-volt battery, which is the same voltage that we're using in the sketch. If you want to rotate it, you click on the component and then press R on your keyboard. And then we're going to pull 3 resistors. Now, if we look back at the resistors that we were using, it was 3, 10, and 5. And this is K ohms. We're going to make sure that we're putting it on ohms. And 5. Okay, so let's connect this. You could try to make it, pretty if you want, but we'll try to do our best to make it look good. So now that we have it connected, we're gonna pull up the multimeter. And then so this is another concept that's really good for you to understand if you ever do have these things in real life, is that if you have a voltmeter, then you want to connect it in parallel to that component that you're reading. So for example, this resistor, if we were to want to find out how much voltage drop is across this resistor, then we would connect it in parallel. The reason being is that if we were to give this voltmeter a very high resistance so that no current is passing through it, then we're going to be also getting the exact voltage that's going across it. And you could go back to Ohm's law to understand what that means. If you have a high resistance, then there's not going to be current going through there, and then there's not going to be any voltage drop, and we're going to be able to get the actual current that's passing through here. So if we go back to the sketch and we see how much voltage drop was over VR1, it's 1.5. Now, reason we're getting 1.38 are possibly 2 reasons. One could be that the battery has internal resistance, which is something that I talk about here. So batteries usually have internal resistance. The reason that they have internal resistance is because not all batteries don't come with 100% conductivity. There's materials in the battery that aren't 100% conductive, so you're going to be losing some power through that stuff, or you're going to have resistance that's going to take away from the actual EMF, which is the 9 volts, and then the terminal voltage is a little bit less than that because of that internal resistance. Or it could be because the voltmeter by default or from the market, it comes with some internal resistance itself, which is like very bad in some cases because you're not going to be able to get an accurate reading. Now that we were able to check that, we know that that's correct. Now if we were to want to check what the current is, then we want to connect this in series. And why we want to do that is because if you remember, whenever you're in series, the current is always going to be the same throughout the whole path or the whole wire. So if we change this to amps, we're going to get an amp of 462 milliamps. And if we look back at what it is here, it's 0.5 amps. So we can see that there's still a little bit of current lost, whether that be from the internal resistance of the battery or from the resistance that the voltmeter might have or the multimeter might have. Cool. So now that we talked about that and we showed you how you could actually scan or measure some of these components, we're going to go ahead and talk about the parallel connection, which is the other type of circuit that's usually analyzed whenever it comes to circuit analysis. So with parallel connections, as you can see here, we have a battery and we have a bulb that's connected between 2 branches of wires. So that's basically what a parallel connection is. You could definitely configure these wires in a different manner, but as long as you have branches that are connecting from one component to the other, and they're not all direct, that's essentially a parallel connection. The cool thing about this is that with parallel connections, is that between each junction of the wires being split, the current is being split as well. But wherever it's split, it's going to join back at the other junction. So current flowing into the junction from a path that splits is going to equal the one that flows out, or the current that flows out. And because of that, well, not because of that, but in parallel connections also, all the components that are within that connection are going to be the same voltage. And the reason that is because since these wires are essentially connecting from one junction, they're used, it's the same wire terminal for the positive as it is for the negative. And I'll show you another example in the next slide. So this is another example, and like you can see on this bottom example, this wire and this wire right here are essentially having all these be the same. So this is the positive wire and this is the negative wire, which is why the voltage across these are all the same. So I'm gonna ask you guys another question when it comes to reading resistors or trying to get the equivalent resistance of the whole system when you have a parallel circuit. How is it that you add them? Let's see if anyone. Yeah?
Some of the reciprocal.
Exactly, some of the reciprocal. So the reason that is that if you were to want the current of each of these resistors, it would be V over R1, where the V is the same because the voltage is the same in parallel connections. Since the V is the same, we could just cancel out that V and have it be a 1, which is why 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over R equivalent. So in this case, it would be 1 over 10 plus 1 over 2 plus 1 over 1. And that would equal 1.6 ohms. And then if we were to want the resistance equivalence, then we would have that equal 1 over 1.6, which would equal 0.625. So essentially, we're creating one resistor from these three resistors, and the resistance of that is 0.625. The reason we do that now is because we have the voltage and we have the resistance equivalent, so we could find the current that's going through the whole system with that specific resistance. So with that, we would get the voltage and divide it by the resistance that we have to get the current. And that would equal 14.4 ohm or 14.4 amps throughout the whole circuit. With this value now, again, we can find we already know that the voltage is going to be 9 volts for every single resistor because it's in parallel. So then the only other thing that we could find from this circuit is the current that's going through each circuit. Now, if you guys remember when I talked about current, the current, it flows in such a way where more current is going to flow where there's least resistance. So it's pretty straightforward question or answer, but the resistance or the current is going to be the most when the current is the least, right? So in this resistor, we're going to have the most current. In this one, we're going to have a little bit more. And then here, we're going to have the least current passing through this resistor. So as you can see, we have the least current passing through the 10 ohm resistor, which is 0.9 amps. And for the second one, 4.5 amps. And as you can see, the voltage is the same. We're just dividing the voltage by the resistor to find what that current is. And if we were to add the current that's going in through each one and then coming out is going to essentially be the same current that was brought into it, which is something else that we talked about in the prior slides, where the current that's going through one junction is the same current that's going to be leaving those junctions at the end. Now, what we're going to do again is check to see that this is true. In this case, we're going to be using another website, circuitlab.com. Now, the reason that we're going to be using this other website is because when you do it in TinkerCad, it doesn't come out correctly. The theory of the parallel voltage being the same, it's not true. So I think that may be because of the battery, but in this case, we're going to be using a voltage source that's going to show us that that theory is true. So if you go to circuitlab.com, you'll have this. Just go ahead and highlight everything. And then we're going to pull up we're gonna pull the voltage source with 3 resistors. If you guys have any questions or if I'm going too fast or anything, just let me know, please. I've seen some batteries represented by 2 lines instead of 4. What's the difference? A battery represented by 2 lines instead of 4. When you say that, do you mean like this? Instead of 4, I don't know what exactly.
On the circuit diagram you show, it's like a long line, short line, long line, short line, but I've seen some that are just a long line and short line. Is there any difference between those 2 types of batteries, or is it like just different way of drawing it?
Yeah, there's a lot of different ways of, there's no difference. There's a lot of different ways of drawing circuits. It's usually easier, I believe, with the 2 lines, but it depends how it is for you or what your preference is. But whenever you have a circuit that looks very complicated, there's ways of reconstructing that circuit so that it looks a lot more easier to understand. And I've definitely gone through that when I took circuits 1 and 2. It's pretty interesting, but it could also be a little bit confusing at times. So if we look back, it's 10, 2, and 1. So let's connect these wires together. 10, 2, and 1, and the voltage here is 9. And then also something to remember is that whenever you're working with circuits, you always want to have it go to ground, because this ground is a reference point that if anything were to happen, we have a ground connected, so it should be good to work with. So now that we have that, we'll use the voltmeter. And as you guys could remember, what I talked about the voltmeter is that we want to connect it in a parallel so that we could get the voltage that's connected or being passed through all these. And as you can see, we have 9 volts, which is true because, like I said, this being parallel is always going to be 9 volts no matter where you connect it to. And now if we want to connect an amp meter, we want to connect this in series. So let's do it here. Actually, not there. Here. Let's flip this over so we get the right polarity, and we got 13.5. Now that's true because if we remember how much current went through R1, or the 10 ohm resistor, it was 0.9. Is that correct? 0.9. Yeah. And we could actually check that. So let's do this. Yeah, and that's exactly what we got. So as you can see, that's the way that current works, in which in one junction it's getting split up, and at the end of the junction it's going back together. And same thing with the voltage. The voltage is always going to be the same. Since we haven't reached past the junction that goes from R3, the amp reader reads the amps from R2 to R1, R2 plus R1. Since we haven't reached past the junction that goes to R3, yeah. Well, no, it's gonna read the junction. It's gonna read the junction that's past R1, but the current that's still going to R2 and R3 is 13.5. So 13.5 is gonna be divided between R2 and R3. You get what I'm saying? Yeah. But like, let's say if you were to put the amp. Oh, what is this? Let's just do this. If we were to put the amp here, we would get 9 nanoamps, which would be correct. Is it 9 nano? Am I looking at that wrong? No, yeah. So basically that's how current works and voltage works in the parallel circuit. And we checked that with circuitlab.com. These are really good resources if you ever have circuits that you're working with and you want to make sure that you're reading them correctly. So now that we've done that and we got a little bit more familiar, why would it be nano? Oh, I'm stupid. This is connected to the voltmeter, so we have to connect it here. The 9 nanos are the current that's going through the voltmeter, because if you remember a voltmeter, the resistance is always going to be very, very high, so that the minimum amount of current is passing through it, so that we could find the voltage that's going through all of them. Yeah. So what I meant to do was putting the amp reader here. And we get the 9 amps, which is correct if we look back at this. But that's there to show you exactly how the voltmeter works, and that the resistance of the voltmeter is always going to be very, very high, so that you're not getting any current or very little current, so that you could read the voltage very accurately. So yeah. So now that we are here, we're going to be playing with the microbit. So what the microbit is essentially a very tiny computer that encourages young people or people that are just getting into programming to learn how to interact with different hardware components. The cool thing about the microbit is that it has a LED matrix, so you could create different faces or different figures depending on what it is that you're doing. In case of a compass, if you were to use a compass, you could put an arrow, which is something that we're going to do, or if you have an alert, you could put an X or an exclamation mark. But you also have a temperature sensor with the microbit. You have a Bluetooth if you want to connect other microbits, and an accelerometer. So starting off, we're going to do one of the sketches, which is going to be the thermometer, or thermometer or sketch. So we're going to be able to get the temperature of the actual microbit, and then we're going to display it on the screen, and as well as we're going to be using a servo so that we could, in essence, show that when something is hot, when something is cold or normal. Something cool about the servo for you to know is that it's essentially a potentiometer, which is like a scroll wheel, or the things that you use to change the volume on your headset maybe, or things like that. And it goes by degrees. Yeah, it goes by degrees. So it goes from 0 to 90 to 180. So let's go ahead and pull up TinkerCad again. Where's my TinkerCad? Okay, so we could go ahead and delete that by pressing Shift, or stop the simulation, then press Shift and highlight everything. You could delete that. So we're going to start by bringing up the microbit. And then for this microbit to work, or not, for the servo to work, we need batteries. Now you could also use batteries that come, or the voltage that comes from the microbit itself, but so that we could play around with the batteries as well, we're going to be using the battery 1.5 volts, and then we're going to make sure it's the type AAA. And you could also put a switch if you want, but in this case it's not really going to be that necessary, because again, like I said, you could use the 3 volts on the microbit. And then we're going to pull up the servo. And then from here, essentially what we're going to be doing is so the servo will tell you what wires are going to be used for what. So this is for ground, so we can connect that to the ground on the microbit. And we can change it to black so that we are a little bit more color coordinated. I can't talk right now. But then you connect the positive to the batteries, and then the negative on the batteries to the ground as well. And you could connect this to any of the signal bits, but this orange wire is going to be for the signal. So now that we have that, we're going to be playing around a little bit with the block code that comes with TinkerCad at this point. So if you aren't very familiar with programming, this is going to be great for you. If you aren't, this should be easy for you, easy breeze. So something else to mention is that like Arduino or Unity in some cases as well, you have your start method and your forever method. Your start is the method that, yeah. So you have your onStart method, which is the method that's going to be run as soon as you start the simulation, and it's going to be like if you have to declare something, or if you have a variable or that type of stuff, and then forever is going to repeatedly continue to execute. So in this case, what we're going to be doing is we're going to start off by plotting. We're not going to be using the start at all, so we can go ahead and delete that. But we're going to be showing the display, the temperature that is reading. So for that, we're going to use the output block, and then we're going to go to plot graph. And then what we're going to be plotting, if we go to input, the input that we're getting from the microbit is going to be the temperature, right? So we're going to do that. And just to show you, let me see if it shows. Just to show you, the temperature is going to go from -5 to 50. So that's why we're going to be putting this temperature up to 50. So it's going to be able to show you on the display going from 0 or -5 to 50 degrees. And from here, we're going to go ahead and have that temperature adjust what the servo is doing. So again, we're going to have to get an output, and we're going to use a rotate servo method. So if we look at what pin we connected the servo to, it's pin 2. And then we're going to get the temperature input again, and we're going to do some mathematics with this. So we're going to be adding the temperature plus 69. And the reason that we're going to be doing it that way is because we want, since the servo goes from 0 to 180, it's not going to reach exactly 180, but the way that we're doing it, it's making it so that once we place these little error notes, we're able to tell it whether it's hot or cold. So you could actually get an emoji from one of those emoji websites, or you could just put the temperature. And then essentially what this is going to do is that when we change the temperature, it's going to be pointing at what it is, and it's going to be showing you the graph. Now, not only can it show you the graph, but it could also show you the temperature, like I said. So what you could do here, if you go to output and show number, let's put this here and then put temperature there, and it's actually going to show you the temperature that it's reading currently. So if you put a 50, we'll see 50, but you, like I said, you could also use the bar graph, and you could also show strings, which is pretty neat. So that's the first sketch that we're doing with the microbit. The next sketch is gonna be a compass sketch. So essentially we're gonna be doing the same thing or something similar in that we're using the forever loop, and in this case we're gonna be creating a variable which is called angled, and we're gonna be getting the compass heading, which is the variable that the compass gives us depending on the reading, and then doing some calculations so that we could floor that value and get from 0 to 7. Now, similar to programming in general, there's multiple ways of coding something. You could have an if statement after an if statement after an if statement, or you could have an if statement within an else, and within that else having another if statement that checks that condition. Depends all to your preferences, really how you want to do it. If it's easier for you to read it like this, then that's the way that would be better for you. If you prefer using the else statement, you can do that as well. So let's go ahead and do that really quick. In this case, we're not going to be needing any of the components, since we're just going to be using the compass reading that's coming directly from the microbit. What time is it? 40. And I might go a little bit quick on this one just so that we have enough time for the Arduino programming, because I also wanted to show you guys the ultra distance sensor. So essentially what we're going to be doing is we're going to be creating an angle in this So we're going to create a variable that's called angle. And then we're going to be setting that angle depending on the compass reading that we get. So for that, we're going to use math. I'm going to use math twice, one to add and one to divide. And so we're going to get the input, which is the compass heading. And we're going to be adding the compass heading, which is the degrees of the compass, by 2.5. And then we're going to get this value. And then we're going to divide it by 45. Another thing that we're going to do, one of the math operations, is we're going to be flooring it. If you guys know what a floor is, basically whatever value it is, closest to, if it's a decimal, for example, 3.5 is going to be 3 if we floor it. So this is going to essentially make it so that when we create those if statements that are checking from 0 to 7, this floor is going to make it so that the degrees that are showing up on the LED are correct. So at this point, we're going to use multiple if statements, and we're going to check to make sure that the value is going to be 0 to 7. Starting off with 0, and then we're going to use that angle to check that. So since we're going to use this multiple times, we're going to go ahead and duplicate it very, very much. And if you go from the top of it, then you're going to be duplicating that many. In total, we're going to be needing 8. So just make sure you have 8 if statements in total. And then from there, just make sure that you change the value that you're checking from 0 to 7. And I'm going to do an example in terms of actually doing the calculation so you guys can see how the value is being checked. Let me bring up the calculator really quick. Let's say, for example, you were to get 80 degrees, right? You add it by 2.5 and then divide it by 45, you'll get 2.27. If you floor this, you get 2. So the angle that you're going to be getting is going to be within this if statement. From this point, we're going to be using the output, and we're going to be showing different LED displays or LED matrix displays on the microbit. And this is essentially what's going to create that arrow that's going to tell us where it's pointing. So you start off from the top, and then you go to the, is it northwest, northeast? I'm not so good with my directions, or my northeast, west, south, whatever. That's what, I mean, unfortunately I need to use the GPS whenever I'm driving, unless I'm like in my area that I know. But anyways, we're almost done with our microbits, and then we're gonna get into the interesting stuff. This is more so, this is interesting as well, but this is more so for the people that aren't really familiar with programming and want to get more familiar with it. And if we run this, and we click on this button right here, this gives us access to the compass. Now, if we were to look at the orientation of the actual microbit and look at the direction that it's pointing the arrow, then it's executing correctly. It's doing what it is that we want it to do. So if we were to point directly on top of the logo, then it's showing us 0 compass, which is going to be a 0 value. Pretty cool. So, because we don't have a lot of time, it's already 45 minutes, we're gonna skip the motion alert sketch, but I am gonna talk to you about some of the components that we're using here so you guys are familiar with it, and if you ever want to do any projects with it, you can. This is the piezoelectric buzzer. What this is using is a white ceramic material. So for example, quartz is one of those materials. And the really, really cool thing about this material is that if you were to hit it like with a rock or with a hammer, it's gonna generate electricity. Similarly, if you were to give it electricity, this material, this rock, this crystal, is going to move. It's going to displace and change like the diameter of the disc that it is. So you cut these in very thin slabs, and they change like shape essentially. And this is what creates sounds from this buzzer. And then this motion sensor is a PIR sensor. What it uses is a piezoelectric sensor, and then it gets readings from heat that humans are emitting. So that's why it's an infrared sensor. It's receiving that heat radiation that we're giving off, which is pretty cool. So if you do want to do the sketch on your own, I'll make sure to give this this workshop or this presentation to you guys, or you guys could maybe screenshot it right now if you want. I'll give you like 2-3 seconds, and then we'll start the Arduino portion of the workshop. Okay. So for the Arduino portion of the workshop, I'm going to talk to you a little bit about what an Arduino is, some of the features that you have and things that you could do with it, and why it's a really, really good source for learning how to program and interacting with hardware. So it's basically an open source electronic platform. So it's a really, really small computer that you can program things onto it. And with that, you're given the ability to use the Gpio pins that it has to read different inputs and send out different inputs. So whether that be using a button or sending out a tweet or activating a motor, let's say you wanted to create a car or a small robot that uses an ultra distance sensor, you could do that. The good thing about an Arduino is that you have a really big open source community. So there's a lot of libraries as well that Arduino has for you. Whether you want to do things with AI or machine learning, or if you want to use different sensors, there's a whole bunch of libraries that makes it very easy for you to prototype and program with it. It's also very, very, very cheap. You could get the original Arduino, or you could get mocks or like clones of the Arduino that you could maybe get for $5-10 on eBay or something, or on Amazon. There's also really, really cheap Arduinos that you can find. And it's multi-platform. So the IDE that comes with Arduino, you're able to use it on multiple platforms, which is really, really good. STM32. That's funny. But yeah, and the good thing also is that they recently came out with an updated version of their IDE, which is one of the biggest updates that they've had. It's still in beta, but it's very good and different from the ones that they've had prior. And to talk to you a little bit about the Gpio pins, there's a lot of different pins, or not a lot, but there's 4. You have the digital pins, the analog pins, and the power, and then the communication pins. So with the digital pins, Arduino being a digital device, you essentially are going to tell the code what you're going to be using that pin for, whether it's going to be an input pin or an output pin. But with these pins being digital, that means you're either going to get 0 volts or 5 volts. A low or high, or things that are binary. So whether that be turning on an LED or turning on a switch or something. But you also have analog pins. Now the analog pins are only analog in pins, so these are things that are going to read like the potentiometer. And then you also have your power pins. Oh, one thing to mention with the analog pins is that you don't actually have to declare these pins like you do with the digital pins. Whether you're going to be using it for out or in, because since the analog pin is only a read pin, then there's not really any point in that. But you can still do it if you want to keep the convention. And then power pins, whatever modules or components you're going to be connecting or sensors you're going to be connecting to the Raspberry Pi, you want it to have power, right? So that's what the power pins are going to be for. It's a great, yeah. No, that's super, super interesting. Only $5. Wow. That's interesting. Yeah, I think maybe we should do a STM workshop. I'm sure a lot of people would be interested in that. And then you also have your communication pins. So these are protocol communication pins that allow you to communicate with specific devices or modules. So take, for example, an LED strip or a motor driver. If you want to communicate with multiple Arduinos, then you would use these pins to communicate to them. And these are the gray ones that are highlighted here, the I2C, the SPI, and the UART. These are different protocols, each having a different characteristic in the way that they communicate through the bits and the wires that they use. Because like, I think the SPI uses like a direct, it's like a slave master type of communication, and then others use like direct wires. But that's a little bit more advanced, and then essentially maybe later on we'll get into that. But to start off, we're gonna do the Hello World version of Arduino programming, which is blinking the LED. So let me go ahead and do this. to make it better for you guys and for me. So go ahead and open up your TinkerCad as well if you want to follow along. And then we're going to go to circuit and we're going to create a new circuit. So for this sketch, we're going to be taking an Arduino, and then we're going to be taking an LED. Something to mention about whenever you're playing with LEDs is that you're always going to need a resistor, because these LEDs, if you don't give them a resistor, then they most likely will burn out. And the resistor is going to make it so that the current that's going into the LED is not a lot and is not going to burn out on you. Another thing to mention is that LEDs usually have a positive and then a negative. The positive is an anode, and then the negative is a cathode. So the anode, you're going to connect this to the resistor, and then from the resistor to the pin that you're going to be using. In this case, we're going to be using 13. You could color coordinate it if you want, so you could know which ones are the positive and the negative. In real life, the LEDs, the longer pin is going to be the one that's positive, and then the negative is going to be the one that's shorter. You could also, with TinkerCad, use block coding if you want, but in this case, we're going to practice a little bit with text. And then by default, because we made that circuit such the way that we did it, it's going to create it for you. Something else to mention is that LEDs in general have this LED light right here that's connected to that pin 13. So if you don't, for whatever reason, have an LED light and you still want to play around with that LED, you could do so with the one that's built on it. So similar to how it was with the block code that we did for the microbit, you have your setup and your loop. So the setup is going to run once when you start the simulation, and the loop is going to continuously run, right? This disappear? Yeah, it did. So since, like I said in the beginning, when we're going to be using those pins, we have to specify what pin we're using and what we're using it for. In this case, we're going to be using it as an output pin. Since we're going to be turning on an LED, we're sending the signal to LED. And then we have the digital write method that is comes with the Arduino IDE or the language. And this is essentially giving that LED a low voltage or a high signal or a low signal, which is going to be basically telling it to turn on or turn off. And so that we can see that the difference in when it's on and off, we're going to be giving it a delay. These delays go by microseconds, so this is essentially going to be 1 second. And then we're going to be telling it to turn off with a low. These high and low values that we're giving it is also custom to Arduino and the IDE. Is essentially telling the digital write parameter that it's going to be on or off, and then we're going to give this same delay to it. So if we were to run this, we would see the LED here, and like I said, on the board as well, turning on and off. Pretty cool. So now that we did that, we're going to go ahead and talk a little bit about PWM, or pulse width modulation, and we're going to be doing another sketch, which is the fade LED sketch. Now what this is going to allow us to do is make the LED go from very dim to very bright, and then from bright back to very dim. And the way we're going to do it is by using a for loop. Now, something that you have to understand is, since the Arduino is a digital device, it doesn't take analog signals. We're going to be using the PWM component or functionality that the Arduino has to take those signals that we want to give the LED and make it more act as if it's analog. And the way it does this is by something that's called the duty cycle. So what the duty cycle is essentially is telling us how long we want the Arduino to be providing 5 volts or 0 volts. And what this is going to do is that depending on how long we want it to be on at 5 volts or 9 volts, or be off at 5 volts or 9 volts, is going to be giving you a different average of what exact power or signal you're going to be giving the LED. So as you can see here, 50 of 9 volts is going to be giving you a 4.5 volts average, and that's essentially what you're going to be giving that LED by using that analog write method. Similar, the same thing with the 5 volts. If you were to give it 50% duty cycle or an analog write of 127, which I forgot to mention, the range of that PWM signal is from 0 to 255, then we're going to be giving it 2.5 volts. And that's why at that point in the program is going to be in the middle, not super bright, but nor is it going to be off. So let's go ahead and start programming this. It's going to be the same pin that we're going to be using. Only difference now is that we're going to be using a for loop. So stop the So we're going to be creating a for loop. It's going to be an int brightness equal to 255. And then we want this brightness to continue to increment if it's less than 255. And so we're going to use that analog write method to provide that LED that value or that signal of brightness. So now we could just go ahead and copy and paste that for loop and change a few things up. Since we're going to be going from very dim to bright and then from bright back to very dim, we want this to actually, the way that I coded it right now is going from very bright. So let's do this. It's going from very bright to dim, so then we're going to do it the opposite. It doesn't really matter. That's what programming is. You create whatever it is that you want to do. And we're going to be also giving it a delay so that we can see better the actual the movement of the LED or the changing of the LED. All right, let's go ahead and see what happens. So it starts very high, goes dim, and then goes back up to very bright. And that's essentially what we talked about with the PWM and using the analog write signal, creating different voltages that the LED is receiving, so that creates different scales of that brightness that you're seeing. Now, I also did have a potentiometer sketch that I wanted to go over. It's not too much code, so we'll go through this one really quickly. First of all, let me talk to you about what the potentiometer is. Basically, you're sending a value from that potentiometer, which is going to go from 0 to 1023 because the Arduino has an ADC converter. So since this potentiometer is sending an analog signal, but the Arduino is only a digital, that's why it's using the ADC chip, where it's converting analog to digital, and it's using the analog read to do this. The way it does this is with any analog signal, which is very constant, it's getting a point within that constant signal or value, and then changing it into a binary value. So let's go ahead and first get that potentiometer really quickly, and then we'll do that last sketch that we have, which is going to be the ultra distance sensor, which is also pretty interesting because it uses a trigger pin and an echo pin to determine the distance in which something is, and we'll get to that soon enough. So with the potentiometer, you have the wiper, which is going to be the signal that you're sending the Arduino, but either terminal can be used as a positive or as a negative. So you could either pin you could designate to be the 5 volts or the ground. And then from there, let's go ahead and start coding. So you could make the sensor value equal to 0. What essentially that's doing is initializing it to 0, but we could initialize it in the loop as well. And it's still going to read the same. So also something new that we're going to talk about here is a serial class, and what this is going to allow us to do is communicate with the actual serial monitor. So when you have an Arduino, you have it connected to your computer. So the way that you're having to communicate with that is having a baud rate. This number 9600, it's just a number that's used to reference what it is that you're communicating with, but it could be any number really. And then we could also designate that pin to be an input pin. But again, analog reads are always going to be inputs, so it's not really necessary. So we're going to make this an integer, and then we're going to give it that analog read so that it can get that value from the potentiometer that's being read from that A0 pin. And then we're going to use that serial class to now print it to the serial monitor so that we could read it. And in the Arduino language or the IDE, you have prints and you have println, so that if you want something to print on the new line, then you would use ln. If you just want it to be on one line, you just use it, let it be prints. So now if we check this and we run it, did I write it wrong? I did. When we open the serial monitor and we move this, we'll see that the values are changing from 0 to 1023, which is because of that 10-bit ADC chip that we have on the Arduino. Because 10 bits, if you were to change it to decimal, is 1023. Cool. So last but not least, we have the ultra distance sensor sketch. So to talk to you a little bit about this sensor and what it does and how it works. Essentially, it's sending out a ultrasonic pulse and then waiting to see when it receives that back. Now, the actual way that it works is that you have a trigger pin and then you have an echo pin. The trigger pin is a pin that's going to be sent 10 microseconds of a pulse, and then as soon as that happens, it's going to initiate the trigger speaker or sensor to shoot those ultrasonic pulses out. And depending on how long it takes for those waves to reach something and come back, depends whether you're gonna get an object detected or not. If you don't get an object detected, then it's gonna be 38 milliseconds, which is the timeout limit of the actual sensor that we're using. But in this case, for example, it took this sensor 500 microseconds to receive those waves back. At that point, once it realizes that there's an object, it turns that echo pin off. So the echo pin is an output, and then the trigger pin is an input that we're sending it. And then the way that we're now getting the distance is because since we know that ultra waves travel at the speed of sound, and the speed of sound is 343 micros per second, or meters per second, then we could use that to then use the equation for speed, solve it for distance, and that gives us the duration divided by 2, because since the waves are reaching an object and then coming back, we have to divide it by 2 so that we could get the actual duration of the object. And then we're multiplying it by the speed of sound. Yeah, correct. So now that we understand how that works, let's go ahead and get that ultrasonic sensor. Let's take off this potentiometer. Let's add it here. So if we look back at the code that we're going to be using, we can also define specific variables, constants, if we are going to be using these pins throughout the whole project or the program. And that's what we're doing here. We're defining these variables to be 6 and be 5. So the trigger pin is going to be 6 and the echo pin is going to be 5. So then we're going to get the trigger pin. We're going to make sure that it goes to pin 6, was it? Yeah, and then the echo pin is going to be 5. And then VCC is power, so we're going to give it the 5 volts. And ground. Black and red. Now let's go ahead and code this. So we're going to create those constants. And then again, we're going to use that serial communication so that we could communicate to the monitor, and then we're going to define the pins that we're using. So the echo pin, again, if you could recall, it's going to be an input pin, and that's so that we can receive when that object is sensed. And then we're using the trigger pin as the output since we're sending it a value. Okay. So we're going to be using the digital write, and as you can recall, we're going to be first sending the trigger pin a low value so that we could make sure that it is initially low before we send it those 10 microseconds that we want it to read, so that it could then send those 8 pulses that we want it to send out to the object that we're trying to read. And these are the 10 microseconds that we want the sensor to receive. And then the delay is going to be 10, so that it knows after the signal is sent to send those pulses. And then after that, we're just going to turn off the signal. Now we're going to use that formula that we talked about, and we're going to be using a actual method that Arduino has for this sensor, and that's going to be called the pulse in. And this is going to be what's going to be received by the echo pin if an object is in front of it. And then use that formula that we have for distance. And multiply by the speed of sound. Now just print that information to the screen. Oh, let me not forget for the semicolon. And the distance variable is going to come back with actual distance that is being read by the sensor. And this is in centimeters that we're receiving it. And then just a delay so that we can give it time to read everything and then process again. Okay, let's go ahead and run this. Now, what is the issue? Void setup. Serial print equals. Where? Oh, here. Good catch. What else? Equals sign. Anyone catch it? What am I missing? Distance. Semicolon where? Huh? Line 8. Oh. That's the thing about programming. Is there another one? I will spend hours on the program that I wrote just to find out it's a semicolon or something stupid. What is it now? Serial print, distance, duration, echo pin. Did I connect it correctly? I did. You have an extra print. Do you see it though? At the end, 920? Oh, wow. That's annoying. Okay, well, it's working now. Let's do a lens so that we could see each line. And as you can see, if we click on the sensor and we move the object that it's in theory like receiving, which is my mouse, then it's going from very small to very far. And essentially that's how the ultrasonic sensor works. So you could think about this in such a way where if you were to connect this Arduino to different motors that control tires, and then you use the ultrasonic sensor to receive that distance, and if it's something's in front of it, move those tires back. And there's a lot of things that you could do with this sensor, accompanied with a lot of other components. Exactly, and that's one of the workshops that we did last semester for Make, so it was a lot of fun for sure. Detect people, avoid. Basically, yeah. But that's gonna be it. If you guys have any questions for me, or any questions at all, cool. If not, then that was a workshop. I really appreciate you guys coming out and participating and talking in the chat and going along with the workshop and the different sketches.
Is there a specific? Oh,
yeah?
Sorry.
Go ahead.
Is there a specific place you'd recommend to like pick up like Arduino projects or something, or to like look, you know what I mean, like kind of like first starting out like guided stuff or anything?
Yeah. I don't know if they have Arduino projects, but I do know that they have Raspberry Pi projects, and those are very, very good source for me when I started working with Raspberry Pi. For Arduino, I would probably just stay on YouTube, but if you're looking for projects with Raspberry Pi, which I would also recommend, if you want to start out with programming with hardware, you can check out that website. Let me send it now.
Okay, thank you.
No problem. Yeah, but definitely look online and on YouTube, and there's a lot of resources, especially since Arduino is such a big community. You'll find a lot of things out there. And also UPE, if you go back on their YouTube, there's a lot of projects that they've done there with Arduinos and with Raspberry Pis.
Yeah, and if you're doing a project or thinking of a project and maybe you don't know how to start, we're always in the UPE Make chat. You can always come there and just share like pictures of what you're doing and stuff, and we can help you out, definitely.
Could you send me? Is that the previous link that was sent in the chat, or could you send me a link for that?
Are you on the UPE Discord? If not, I'll send the link.
No, I'm not.
Okay, then I just sent it in the chat. You can join there. Then you need to basically set that you're interested in Make. In one of the channels is gonna ask you for that, and then yeah, you can
yeah,
you know, or you can reach out to me. I'm Miguel de Jesus, and you'll see me as well.
What's your Discord, Miguel?
I'll send it here.
You could also reach out to me if you have any questions. Also, if you guys want to drop in your LinkedIn, we could. It's always good to connect. Go ahead and do so if you want to. You can connect with me as well. And you could also, if you have any questions about this workshop or anything in general, or some of my experience, or anyone else in this group, more than happy to connect with you guys. Why does mine always come like that? I think I need to do it with the HTTPS. But thank you guys again. I really appreciate you guys coming out. And yeah, stay tuned for more stuff from UPE, from SHPE, from CAHSI. You know, we got to represent our Hispanics as well. representing from Colombia. Yeah. But all right, thank you guys. I appreciate it.